Hello, everybody. Welcome to the OpenUSD Insiders live stream. We have a fantastic show today. I'm going to jump right into things. We have a quick announcement regarding the OpenUSD training courses, which are available absolutely free. We'll post a link in the chat. So if you're new to OpenUSD, you're just learning about it, or you're a veteran, the OpenUSD Learning Path has great module separated into several levels, many of which are available right now. That you can learn fundamentals of OpenUSD and get your development kind of started leveraging OpenUSD in your workflows. So we are super excited today to have a live stream specifically regarding Isaac Lab and OpenUSD. So we're talking about accelerating robot learning today. As many of you may know already, Isaac Lab is an open source framework built on NVIDIA Isaac Sim. And its main design is to simplify workflows for reinforcement, imitation learning, and more. As a successor to Isaac Sim, it complements platforms like NVIDIA Isaac Sim and MuJoCo, making it ideal for training robots in tasks like locomotion, navigation, and manipulation. We have some developers here from the NVIDIA team. We also have a very special guest from the 1X Technologies team. So let's get started and bring our guests in right now. Let me stop my presentation. Hey, Ayundamola, how you doing?
I'm doing all right. Hi, Edma.
Why don't you introduce yourself, and then I'll bring in our next guest after you're done.
Okay. Hi, everyone. My name is Oyindamola. I'm a technical marketing engineer for NVIDIA, specializing on Isaac Lab and robotics technology in general.
I'm very happy to have you. And who is this colleague sitting right next to you?
Hey everyone, this is Amulia. I lead product marketing for robot learning, and I'm happy to be here with Oyinda supporting the live stream. Thanks, Edmar.
Awesome. Well, very grateful for your presence here. And of course, we have the 1X team, as I mentioned earlier. Look at these from their offices live, which I believe is not too far from NVIDIA headquarters, if I'm not mistaken.
That's right down the road.
Awesome. So tell me, who's joining us from your team today?
Yeah, I'm Jack. I'm a research engineer at 1X. I work on some of our world model efforts. Eric is going to be joining us in a bit, but
yes, and I'm Daniel. I also am a research engineer. I work on road modeling and evaluation. I'm happy to be here.
Awesome. So we have a great live stream today, everybody. We're going to be kicking things off with an overview of Isaac Lab. We're going to be talking about how you can advance robots with OpenUSD, go through some of the core features of Isaac Lab. We're going to show a nice demo and applying Isaac Lab for various robot embodiments. When 1X is going to show us a really cool video they shared, as long as a slideshow presentation we've got. So let's get right into it. If you're watching the stream from any of the platforms like LinkedIn and YouTube, and you can comment, feel free to ask your questions or comments in the chat. We are going to be watching those throughout the live stream. We will do our best to answer some of those in real time. Otherwise, we'll kind of put a mark next to them. We'll try to hit them later on as the live stream progresses, and we take time for more Q&A. But feel free to post your questions and comments as the live stream moves along. All right, so I think we're going to get started with Amulia with kind of an overview of Isaac Lab and how it helps robot learning challenges. So Amulia, what would you like to start today off with describing to everybody?
Awesome. Thanks so much, Edmar. So the thing is that, robot learning in general has been pretty much challenging. And the reason is because most of the pre-programmed robots tend to hit limitations, especially once they're deployed. It's hard for them to kind of be more adaptable, right? Bringing in a new skill within a robot. For instance, a robot might learn how to move a pallet from point A to point B, and the next thing they need to learn how to manipulate an object. For instance, packing, let's say, your next Amazon order, for example, right? So there's so many ways that these robots need to understand how to build skills, and one of the key ways to do that is a simulation-first approach. And with that, I'd like to get started with the presentation. Let me quickly bring up my slides in here.
Awesome. I see a lot of great regulars watching us, including an Omniverse ambassador, Scott Dempsey. Thanks for joining us today in the chat. Okay, and I'm going to add, let me know when you're ready.
Yes. Are you all able to see my screen?
Yes, yep. If you want to switch to presenter mode. Perfect.
Awesome. So as I mentioned, pre-programmed robots have several limitations, right? And as we're advancing a lot of the applications and running robots across factory lines and warehouses and even hospital facilities, these robots need to do a lot more than what they used to do previously. And some of the key limitations have been around adaptability, the complexity with which these robots have been built and reprogrammed, and then there have been a lot of gaps, especially on the data side of things. And one of the key ways that we see, is going to be a new playing field for robots is getting trained in a simulation-first environment, which is where Isaac Lab comes into play. So Isaac Lab is essentially an open-source robot learning framework that kind of helps you train your robot for different policies and then deploy it in real world. One of the cool things I wanted to talk about is that this is not something new that NVIDIA has built up overnight. We've been doing this groundwork for years. We started out with Isaac Sim. So Isaac Sim launched in 2017. A lot of researchers have built really cool projects using Isaac Sim, and then on to improvise on our developer experience. We brought in the reinforcement learning environments within Isaac Sim. And to go even further, we decided that Isaac Lab, which is kind of the evolution of Isaac Sim, we decided to launch that as a standalone open source component earlier this year. So we announced Isaac Lab at GTC March of this year, and we recently launched Isaac Lab 1.2 in November. In fact, it was last week at Coral 2024. So with that, I want to say that we started out the groundwork with Isaac Sim, and then we went all the way to launching a standalone open source robot learning framework with Isaac Lab. So if you have been previously using Isaac Sim, you could take a look at our migration guides, which our team Amelia and Edmar will share during this presentation. With that, I think you all are kind of familiar that this huge push around simulation first approach, right? Because you tend to save a lot on reprogramming your robots using the physical hardware. There's just so much of intensive work that's involved that doing so in a simulation first environment makes the most sense. So Isaac Lab is essentially helping you build policies that can be deployed on any robot. So whether you're building locomotion policies or you want to build an interesting large-scale data set, we have a lot of examples that my colleague Oenda will share very briefly. But essentially, Isaac Lab is for training any robot policy and deploying it in real world. And Isaac Lab is built on NVIDIA Isaac Sim. We do have monthly robotics office hours, so you can come back and learn more or deep dive into Isaac Sim as well during another session. But the rest of the session will be focused on Isaac Lab and really just setting out with the foundations of what Isaac Lab is, the key features of Isaac Lab, and then we'll talk a little bit about world models and what 1X has been working on. With that, I'd like to pass it on to my colleague Oenda. Go ahead.
Thank you, Amelia. Okay, thank you, Amelia. So I'm just going to go on to the features of Isaac Lab. We've heard different or something about Isaac Lab. So let us deep dive in. What exactly do we have to offer? Okay, first thing to note is that Isaac Lab is modular. We have different kind of APIs and libraries for you to be able to build your assets, to be able to build different kind of tasks that you want to do. So if you're working with manipulators, humanoid, quadruped, we have those asset available, both rigid body asset or deformable asset. And then we have tools available for you to be able to design the environment you want to use and real-time physics. So physics is our physics engine that we use in NVIDIA to be able to simulate and to be able to design and simulate physics of this asset in real time. So Isaac Lab provided those APIs to be able to interact with those assets. And also we have the flexibility of using either reinforcement learning or imitation learning, which are the two main robot learning algorithms that we support with Isaac Lab. So either imitation learning, where you're trying to teach the robot to be able to do something based on human demonstration or video demonstration. We have all of that too. And also for reinforcement learning, we support different kind of libraries, things like RSLRL, stable baselines, or any of those algorithms that you use or If you want to build your own custom algorithm, we have that too. We have that also for you to be able to use. Isaac Lab is scalable, which means that you can actually train it. You can actually do your training over multi-GPU or multi-node, or if peradventure you want to train in cloud, that support is also available. And the environment cloning APIs help us to be able to train multiple of a lot of environments, like thousands of environments in parallel. And that helps to be able to reduce the time for training. So you can actually crash, say, training for like a week, or to like, let's say 4 hours, or training the quadruped to work in like 10 minutes with the environment coding APIs for us to be able to do that. An interesting feature that we have in the current release of Isaac Lab is called tire rendering API, which I'm going to go deep dive later in the next slide. Can you get the next slide, please? Okay, so in Isaac Lab, we have different robots available, over like 16 kind of robots that we have available. And then we're trying to also increase the number of robots as time goes on, because it's also open source, where we welcome communities to be able to design their own robot and also bring it into Isaac Lab. So from MuJoCo style robots, which are the classic robot, every intro to reinforcement, every intro to robot learning, with the first thing that you probably have to interact with, like catpole or humanoid and MuJoCo style robot. To fix arm or hand, UR10, Franca, Allegro, Shadow Hand. To quadruped, we have different kind of quadruped from different companies like Anybotics, Animal, Unitary, Go 1, Go 2, and also Boston Dynamics Spot is now featured in Isaac Lab. We also have humanoid examples like Unitary H1, Unity G1, and also if you're looking into like area manipulation or area systems like quadruped, we also have Crazy Fly robot in Isaac Lab. So if peradventure you're like, okay, I don't want to use any of this, but I want a combination of those kind of robot. For instance, I want a arm, a cooker arm with a Allegro hand, that kind of combination. We also have those kind of available environmental robot in Isaac Lab. We also have different kind of sensors ranging from cameras, RGPD, depth, tight cameras, raycaster, height scanner. For instance, if you're working with quadruped, you need to be able to measure the height, tactile contact sensor, tactile sensor, for graphing, for different kind of tasks that you want to do. So we have all of those sensors that are available. We also have more sensors that are in Isaac Sim that you can actually customize to be able to use in Isaac Lab. And if you have your own custom sensor, we have documentation that are available for you to be able to customize, okay, your robot or your sensor for you to be able to import in Isaac Lab. Can we get the next slide? So in terms of robot learning, one thing that's important for you to do is to actually design your environment. The question is, what kind of tasks do you want to do? Are you trying to manipulate something? Are you trying to navigate? Are you trying to move? Or are you trying to, have different kind of robots, two different kind of, or multi-agent kind of robot to be able to interact together? So Isaac Lab already provide you with baseline tasks. We have more than 26 environments. Right now, I think this number is going to skyrocket after this live stream, because I know a lot of people want to actually develop more environment and bring it into Isaac Lab. So from dextro manipulation, whereby you have a manipulator trying to move either a rigid body or a deformable body from one place to another, or trying to like, for instance, you have the Allegro hand or the Shadow hand trying to move the cube to a particular kind of location, or to legged locomotion, both for quadruped and also for humanoids, walking on both flat terrains or walking on rough terrains like staircase, or different kind of terrains whereby it is not exactly straight or smooth, to navigation, moving from point A to point B, like for quadcopters, maintaining certain height when they over from one point to another point. Then we also have what we call the tire rendering, which is what we call the visual-based RL. So most of the RL, you use things like physics-based observation, probably the position, the velocity, and all of that. Now, incorporating images into your observation, it's a highly computationally expensive task. But one of the things we've come to do is with the availability of different kind of tools that we have in Isaac Lab, we've been able to successfully provide environment that uses vision into the observation. And then I'll talk about that in the next slide. So we have those environments. We have one for the hand, and also the other one for the catapult using like the depth sensor or the depth camera or the RGB camera. Those environments are there for you to be able to test with and then to be able to deploy your own. Now, interestingly, multi-agent system is of quite interest in the robotics community. You want to try to use either two hand or maybe a manipulator and a humanoid, or a quadruped and a humanoid. Those kind of examples. Or you want to use multiple humanoid or multiple quadruped to be able to like work in a particular kind of space. That's when we come to multi-agent reinforcement learning, which is not necessarily the same thing as just having single agent in an environment. It's more complex than that. So we've been able to create an environment for multi-agent reinforcement learning for users and developers, to be able to look into, explore, and then see how you can use this to be able to develop your own tasks for you to be able to do. Then another thing is teleoperation and imitation learning. We all know that imitation learning involves getting data either from videos or teleoperating either the robot to be able to do a particular certain task. We also have that environment created for you to be able to explore and to be able to develop from there. So these are the environments that we have. Let's go to the next slide, which is for us to be able to do robot learning, just to do a backtrack or how we think about robot learning. The first thing you need is a data generator or a renderer. So for robotics, it's a simulator or a real robot. Now, when you have those data, either you're using online reinforcement learning or offline imitation learning, where you're trying to generate your data, then you can train with the data. You need a accurate physics simulator for that. And for us in NVIDIA is what we call Isaac Sim. So Isaac Sim is our reference application for us to be able to design, test, simulate physically accurate virtual AI-based robot, for you to be able to generate this data. Now, if you have this data, how do you train? We create different kind of environment, task design environment. So if you want to do something in robot learning, you call it a task. Then how do you define your tasks? How do you tell the robot what to do? For instance, how do you define the reward function for reinforcement learning? Or how do you define what are the observations, what are the actions that the robot wants to do? So all of that is design is put together into what we call the task design environment, which are Python APIs for you to be able to interact with the simulator and also to be able to train the environment. And that's what we call SIGGRAPH. So SIGGRAPH is a reference application, which is open source, modular, flexible, and scalable for you to be able to interact with your data and the robotic simulator or the real robot. Then we also have robot learning algorithms. So if you have your task design, you have your data, how do you train? So you have different kind of algorithms. So SIGGRAPH also gives you like wrappers for different kind of algorithms, like stable baseline 3, RSLRL, RGames, RoboMimic for imitation learning. Then also you can also design your own custom algorithm. So we have wrappers that link to those open source training libraries for you to be able to use. So we see a whole complete package from data generation, data creation, to designing your tasks, and then training your robot to be able to do a specific task that you want it to do. So those three pieces or three key puzzle pieces of robot learning is provided for you by NVIDIA and also in collaboration with different open source algorithms for training. So if we want to go diving into the next slide, into what exactly is the simulator. That's NVIDIA's Isaac Sim. So we're looking at sim first development. One of course, the core reason for doing simulation is to be able to save cost, is to be able to test different kind of things. If the robot breaks in simulation, that's okay. But if the robot actually breaks in the real world, that's not okay at all. So we can actually test different kind of environments, randomize different kind of parameters, mass, gravity, velocity, position, different kind of things in simulation. That's one thing why we need to actually look at, okay, well, how do we do this in simulation? So Isaac Sim is developed for us to be able to test and simulate. We have different kind of data that you can generate. That you have URDF card data, or you're importing your robot from MuJoCo or from the Gazebo down into Isaac Sim. We have all of those importers for you to be able to use, different kind of sensors, utilities for you to be able to use, synthetic data generation. Like I said, if you want offline data generation, we have that, and also different interfaces for you to be able to connect with either the real world robot or the simulator robot, like robot operating system, ROS1, ROS2, Python. We have OmniGraph and different kind of custom interface that you can actually build. So Isaac Sim is developed on top of NVIDIA Omniverse platform, which uses like OpenUSD to be able to describe most of the assets that's being used. That's universal scene description. Then RTX, RTX rendering for fast rendering of all of the assets that you need to do. We also have physics, which definitely, like I mentioned, with that actually a physics engine that simulates the physics of this asset. So this is built on NVIDIA Omniverse has different kind of awesome tools that you can actually exploit. Can we get the next slide? So Isaac Lab back again. So we have the capability of using back-end multi-physics capability in Isaac Lab, accurate sensor simulation for different kind of environments that you want. It's GPU accelerated, which means that many of the time problem that we have or resource problem that we have using like CPU-based method has been crushed down, has been accelerated using like GPUs. APIs and all. So you can also easily transfer length policy, which we'll probably see later on, is that if you train something in the simulation, how do you ensure that it actually, when you deploy it to the real robot, it actually works? So we have things like domain randomization, whereby you can randomize different kind of parameters in the simulation to ensure that it actually have almost the same attitude or almost the same behavior in the real robot. So you can choose from either deforming object or rigid body object, and then you can create like thousands of parallel environment for you to be able to work with at once. So now back to tile rendering. So like I said before, most of the environment, most of the training that we have, it works with like physics-based environment. Now, if you want to bring vision in the loop into your observation, then you want to try to run like thousands of environments at once. You probably won't be able to do this for, let's say, more than just 20 environments with the previous generation of the simulators that we have, right? But right now we've been able to achieve running over 1,000 of these environments with visual observation in the loop, and that is an incredible achievement for us to be able to run from, say, just 20 environments parallel to 1,000 environments in parallel. So you're able to collect data from multiple camera sensors and simulate them at a go. So this takes like visual input and concatenate those outputs from multiple cameras so that you can have one gigantic image for you to be able to render. So GPU acceleration enables faster robot training, and you can easily configure this API access for, let's say, RGB image. Thank you. Another thing also in Isaac Lab is the flexibility of how you design your tasks. So for most robot learning developers before now, if you're using like, say, different tools like Gymnasium and all of that, you definitely write all your scene creation, your environment scripting, like you define your RL tags, your observation, your action, and also your environment logic, everything in one gigantic script. So that is what we call direct workflow, whereby you have what you see, what you get. You put everything you want in a particular script. So you have a function that is applying action, a function that is doing the +1 reset. You are able to like implement what you want to do or manipulate the environment logic. How does it actually help you to be able to do each of the tasks that you want to do? So that's what we call direct workflow, whereby you have NVIDIA Isaac Sim, you design your scene, and then you do your environment scripting, and then you have the learning agent. Another workflow that we also designed in Isaac Lab is what we call the management-based workflow. This is, you tell us what you want, and when we do it for you. So we kind of break down the approach into different kind of reusable sub-models. So you have a model doing the action management, the command management, the reward management, determination management, observation management, and all. So these sub-models can be easily replaced. For instance, somebody can be designing the observation side, somebody else can be designing the reward side. So you just mentioned, okay, I want position, velocity, this and that. We help you to manage, okay, how does the robot interact with the action that you actually created? How does the robot, step in the environment? How do, termination happen? You just tell us what is the condition you want for termination, and we help you to be able to do all of those things. So management-based environment helps for improved usability, reduce the risk of logic errors. It's faster to implement when a new task, when you want a new task in, because you can easily substitute most of the component. Okay, all right. The next one is scalability. I know I've said a lot of things, so let me kind of slow down a little bit. Okay, all right. I was trying to beat the time, but I think this is good. This is
It's
good.
a lot. It's a lot of information. It's a lot
Yeah,
of
it's a lot of
information,
information.
but
Yeah,
it's great. It's so much detail here, which is awesome. So thank you.
yeah. I'll try to bring it together. So scalability, of course, we want to be able to run on multiple GPUs or multiple nodes. We have the support for that. You can actually scale your GPU in Isaac Lab using the PyTorch distributed framework. I think Amelia can post the Isaac Lab documentation, which has and also the reference architecture, which has like the information on how you want to do that. Also, you can run on cloud, AWS, GPC, Azure, Alibaba Cloud, and things like that are supported for different kind of users. Next. All right. So the next question everybody keep asking is that, okay, this is great. What is the compute that I need to be able to run this? What's the requirement? So the basic requirement definitely you need a GPU that is RTX. A GPU that is RTX enabled is very important. But the first thing is we can run this on Ubuntu or Windows. Though there are some features that may not necessarily be supported on Windows right now, like the multi-GPU or multiple systems. We open a feature that is going to be so Ubuntu either 20 or 22, that's fine. CPU, we have either Intel Core i7 from the 7th generation or AMD Ryzen 7 5, or anything above that is also good. The cores, like the ideal one is 16. The RAM is 64 GB. If you have a 1 TB storage, that's good enough. And also, like I said, the GPU has to be RTX enabled. So anything from RTX 3070, which can be from your laptop or to a desktop or a workstation, you can definitely do that. If a VRAM of at least 16 GB is recommended. Now, of course, if you're doing multiple or parallel thousands or multiple environments at the same time, you want more VRAM for you to be able to use. So the more you have these resources, the faster your training should be able to go. All right. So now let's look at the use case, because the question we ask is that, okay, these are fantastic things that you can do. How are people using this? How are developers using this around? So one of the first one we look at is Boston Dynamics Spot Robot, which was trained in Isaac Lab to work using one of the simulators, one of the environments called the Spot Locomotion environment. That was trained in Isaac Lab, and then it was deployed to the actual Spot working in one of our campus in NVIDIA right here. So we were able to see how sim-to-real gap can be breached using Isaac Lab by doing things like domain randomization, accurate physics modeling of spot in the real world into Isaac Lab. So this is available for anyone to be able to use. Amnia can just post the blog. So a blog was written for us to be able to see how do I start this thing from zero, that's from importing the robot into the environment down to actually deploying it and seeing it work on the actual robot. So that is already put together for us in the blog, and Amelia can just post that on the chat for everybody to see. So we have other other developer like Swiss Mills, ETH Zurich using our Isaac Lab to be able to train a robot dog to move from one place to another place. That's navigation, teaching it new skills on walking on staircase. We also have things that it's not even just the regular locomotion and walking and things like that, or navigating. So we have things like surgical simulation that was built on Isaac Sim and Isaac Lab, and this is an interesting interesting project that brings us into the medical space, how to be able to use Isaac Lab even into the medical space. So this is something that we can definitely explore and then see more on how to be able to use Isaac Lab for that. So not just developers are using Isaac Lab, we also have like companies, humanoid companies using Isaac Lab. So this is Menti. Menti, that's Fourier robot, is being trained to be able to do things like stacking, real world roles, even in from simulation to actually using this in the real world. So we also have like Galbot, building a large scale of dexterous and data sets using Isaac Sim. Menti robot, you can see the Menti tiny robot right there. Not really tiny actually. The dark robot right there in the warehouse, pushing the cart around. So you can imagine, shopping in, one of the shopping stores, or with a robot right there, say hi, what do you want to take, and then the robot say definitely do that. So even on this kind of system, we have Maintain doing that awesome work, there right there. We also have like research teams like Berkeley, Humanity team using low-cost humanoid robot to be able to train the robot on how to do different kind of learning-based control. And also, these are really awesome ways to be able to use Isaac Lab. If you want to get started, because the question you asked is that, how do you get started? You can download Isaac Sim
It's my turn.
and Isaac Lab today. Okay.
Thank you. Thanks, Alinda. Yeah, just a quick correction here. So this is for your robots. This is from Menti. The main thing here is that, Isaac Lab has been used by a lot of these companies and developers. We have folks who are using it to train a policy for quadrupeds, as Oinda mentioned, and also we see a huge potential for using Isaac Lab across humanoid robotics. So this is just a snapshot of some of the examples where, like Galbot has used Isaac Lab to train a large dexterous hand data set. Menti is training in a virtual environment, as Oinda mentioned. And then we also have researchers who are using Isaac Lab to build a low-cost humanoid robotics platform like Berkeley Humanoid. We will share the hyperlinks of each of these examples. You could take a look at the follow-up blogs as well. And again, tying it back to humanoid robotics, right? This is the next generation of robotics where it appears to be complex, and the technologies need to be, like intertwined in a lot of ways, right? So you need data at different layers. So you need live robot data. You also need, like web scale data, because you need to understand the different dynamic scenarios in which these robots need to navigate. And once you have a model, you continue to build on top of it. It could be a foundation model or something that you're building on scratch. And then side by side, you also want to build a policy to train the humanoid robot to today maybe move a box from point A to point B, and tomorrow you might want the same robot to kind of, go across a factory aisle and, pick up something, for a specific purpose, right? So there's a lot of work that's going into data processing and generation pipeline. There's a lot happening on the foundation model side of things. If you've heard of NVIDIA's project GR00T, Isaac Lab plays a pivotal role in helping with the foundation model training there. Again, one of the key things which I am very excited to learn about is from 1X, our partner, who'll be talking a little bit more about world models. What does it really mean, and how does that tie back into, like all things humanoid robotics, and why is it important? I'm really excited to learn more about it from 1X team. Hey, 1X team, back to you. Let me stop sharing my screen here.
Awesome. Thank you both. That was fantastic. Just a quick note that this video, because I know there's a lot of information that's shared there, and there's lots to squeeze in. So this is available on YouTube right away. As soon as the stream is done, you can watch it again. You could slow it down on YouTube if you like. You could speed it up if you're really good. But it's all there on YouTube, and just go to the NVIDIA Omniverse YouTube channel and go under live, and you'll see the stream right there. It's available permanently for people's reference. And thank you both, though. That was really fantastic. We're going to circle back a little bit later with some more NVIDIA information, but we are super honored, as I said earlier, to have the 1X team here. So thank you guys all for joining. I know you have a presentation. I think I could see it now. So you want me to start sharing?
Yes, that would be great.
Okay, here we go.
Great. Hi, everyone. Hello from Sunnyvale. We're the 1X team working on the World Model Challenge. I'm Eric.
I'm Jack.
And I'm Daniel.
Great. So, today we'd be really excited and honored that NVIDIA has brought us onto this live stream. We're happy to share about some of our work on World Modeling Challenge and why we're doing it and how you can help. So yeah, let's start. Can everyone hear us okay?
Sounds perfect.
Great. So a little bit about us as a company. We're 1X. This is a company founded in 2015. We started making a bunch of really, nice, compliant, high torque to weight motors, and then gradually built up the motors into a, humanoid robots. We've got 160 employees globally, with the AI team being about 16 people based in California. So the AI team tries to make the robots do the general purpose tasks autonomously. Just as a bit of an overview of like how our architecture works, we are taking a very modern approach to doing robotics, where instead of the classical sense, plan, act with kind of human design controllers and human design planners and human design grasp primitives, we're doing actually everything learned end to end. So from the balancing and locomotion side, that's trained using RL, very similar to what was just presented previously with Isaac Sim. We are doing end-to-end learned imitation that happens at about 10 hertz control. So that's kind of what you see here in this dexterous planning section. And then at the high level for task and motion planning, we're using modern approaches like VLAs and VLMs to coordinate the selection of low-level skills. And so this is all neural nets, all end-to-end. And with this comes a lot of opportunity. We can potentially, train neural nets to do all kinds of general purpose tasks. But at the same time, there's a lot of challenges because each of these components are black boxes. It can be very hard to reason about whether your new checkpoint is better than your old checkpoint. So I want to talk a little bit about the problem of evaluation. But before that, let me just show you an example of our stack working, like what I just shared. This is a end-to-end learned neural network that's going to go open a door and enter the room. And this was just trained using imitation learning data. So we didn't code up anything in the stack saying what a door is. Or what it means to open the door, or whether you're done or not. It's just all kind of learned from data, and it just imitates what is shown in the data sets. And with enough data, you can actually start to generalize. You can pick up new objects you haven't seen before. You can go into rooms you haven't been in before. And this is how we want to be able to actually scale to the home settings. Here you have several low-level skills that are being chained together. So this is not a single neural network that's doing everything. It is a high-level VLM that is coordinating several low-level skills and deciding when to switch over. So this is an example of how our architecture works for a longer horizon task. Okay, so moving on. Okay. One thing that is kind of not really well known in the robotics space compared to the rest of generative AI is that even though we believe that scaling up data and scaling up compute is going to, and scaling up parameters is going to lead to more general policies, it doesn't always happen that way. So there's some examples of literature where, taking a large data set like OXE, you can find that maybe sometimes smaller models work better than larger models. And then in other cases, sometimes smaller data sets work better than larger data sets. So this is very perplexing and also very scary, because if you're a robotics company betting on scaling, you had better be sure that when you increase these quantities with great costs, that it actually results in a better robot. So yeah, why is scaling important? Well, if we're going to make a big investment into data and compute needed to make a general purpose robot, then you need to be able to predict whether that investment is going to result in a more capable system. So that a lot of people are talking about the ChatGPT moment of robotics kind of being around the corner, and home robots being able to do all kinds of things. But the ChatGPT moment for robotics can only happen once the scaling laws for robotics happens. And what the scaling laws of robotics means is that we have to be able to measure very carefully how increased investment in data and compute translates to improved capabilities. And so we're taking a lot of inspiration from generative modeling. So we see that scaling laws clearly apply in domains like text generation and video generation and image generation. So we're really trying to use as much of the lessons learned from that field as possible and transplant it into robotics, rather than kind of discovering robotic scaling laws completely de novo on our own in a vacuum. So in order to build the scaling laws of robotics, this is actually especially hard to do in robotics, because you have to know how good the robot is at a task. In all the other fields, you can evaluate quickly by running something in a digital computer, and no matter where you are or what computer cluster you're on, you can kind of run and get the same results, more or less. But in robotics, it's very hard, because you need to figure out, you need to run a real robot system in the real world. And we've done these kind of studies where when you train a model and keep the checkpoint fixed, over time, because the environment is changing, the policy can get worse and worse as the environment shifts, or the robot maybe has some change in the visual fiducials or calibration. So this kind of policy decay that we see in the same exact checkpoint really makes it hard to do careful science with scaling laws. So if you train your big model on Monday, and then you train an even bigger model on Friday, it's really hard to compare the two, because you've evaluated them at different points in time. Okay, so I'll turn it over to Jack, who will talk a bit about why we're using the world model to solve this challenge.
Yeah, so in order to address this problem that Eric just talked about, we're working on something called a world model at 1X. And a world model is basically a simulation that tries to predict the future state of the world based on the actions of an agent. And in our case, this agent is our humanoid robot, Eve. And so we've collected thousands and thousands of hours of Eve performing a wide variety of tasks like folding laundry, putting away dishes, pushing in chairs. And then we've used the combination of the videos and the actions from these sequences to train this type of simulation called a world model, which anticipates kind of future videos, which hopefully kind of maps to the real world. And so what you see here to the right is not actually real videos, but generations from our world model. And you really can see some of the richness, such as kind of like this curtain being pulled to the side here reflects some of the deformable mechanics of a curtain, and then the chair being pushed in the bottom right there kind of actually does reflect the mechanics of a chair. And so the idea is, instead of putting these items in a simulation and creating these manual assets, you can just learn this understanding of the world through these videos, and then kind of predict these future states. And so at the real heart of a world model is this notion of action controllability. And so in our world model, we're able to kind of predict diverse outcomes based on different action trajectories that we provide. So in the top row here, we have generations that start from the same initial state, and then we roll out different trajectories, and we see the world really respond around us. So in the case of go to the left door, we see our Eve drive and approach the left door, and then maybe Eve doesn't really want to go to a door and wants to play guitar. So in the middle case, we have Eve playing the air guitar. And then on the bottom row, what we see here is really the main use case of this world model, which is object interaction. And so in the variety of scenarios provided, we have Eve grabbing various boxes, and then these boxes responding in accordance with kind of the gripper's motions. But we haven't completely solved all of the challenge necessary to make this world model useful. The biggest problem we have right now is adherence to physical laws. So in the left generation at the bottom, we see a plate kind of suspended in air, and we all know this should fall to the ground, but the world model doesn't have the understanding yet of 9.81 as the gravity constant. And so another issue we have, as depicted in the middle generation, is object coherence. So we see Eve pick up a red block and try to place it on the plate, but by the time Eve tries to drop it, the object has disappeared. So in order to actually evaluate tasks, hopefully your objects remain in the frame throughout the whole process, which is a pretty important piece there. And then another issue that we're dealing with is kind of handling occluded objects and objects that might not be displayed at favorable angles, and really handling the dimensions of those objects throughout the generation. So there's all of these challenges that we're trying to address, and instead of kind of just banging our heads against the wall internally, we've decided to open up this challenge to the world through a series of tasks that Daniel will talk about.
Sounds great. Yes, I'm happy to introduce our world modeling challenge. It's composed of 3 parts. So we have compression, sampling, and evaluation. And really, this is looking at how we can share with the community, leverage the diversity and richness of these videos that you see on the screen here that we collect with our robot Eve, and how we can turn that into kind of a really useful machine learning algorithm. So the overview of the entire challenge is to predict the future. So in the world model problem, we want to be able to understand the world well enough that we can reliably and accurately kind of foreshadow what is going to happen next. And what we're going to share is 100 hours of raw robot video with state sequences, including kind of what the robot is doing, what the commands that are sent are, and all of that raw video and raw commands will be shared under an open source license. We're furthermore also sharing a video which is tokenized with this new Cosmos tokenizer released by NVIDIA. That's going to be a video tokenizer that temporally kind of processes these 100 hours of data and compresses it into a representation which is kind of more ideal for learning. It's going to be very compressed and discrete, and allow kind of models to interact with them in this embedding space. By sharing these 100 hours we try to make them really diverse and rich videos. We hope that we can train some world models that can predict the future. We furthermore also released some baselines, including using a Llama 3 style LLM to do next token prediction, as well as a Genie model from the Genie paper. And we have a link to the World Model Challenge as well on our GitHub. So for the first level of the challenge, we have a $10,000 prize for this, and it's called the Compression Challenge. And we're really taking inspiration here from kind of scaling, like Eric mentioned, in NLP and vision, where they found that by optimizing a simple loss, in this case, just predicting the next token of a sequence, they could really model really rich and complex interactions. So can we do the same for robotics? In this case, we're giving a challenge to try to minimize the cross entropy loss on a held out sequence of next frame prediction tasks. And the lower the losses or the higher the accuracy on this challenge, the more you kind of can understand and accurately predict what happens next. So in this challenge, we ask, we have a kind of a threshold for loss and for achieving a successful level of compression. And by achieving that, you can achieve a $10,000 kind of bounty. The next challenge is called the sampling challenge, also coming with a $10,000 prize. And this kind of takes the ideas from the first challenge of sampling, of compression, and kind of extracts the actual perceptual image from that next token. So in this case, rather than operating on a token level, you can imagine that given a sequence of images, can we accurately predict what the next image itself is going to look like, scored against just perceptual similarity to the actual future that happened in the real world. So if we can predict coherent and plausible continuations of the future, then that kind of starts being able to become this kind of neurosimulation, which we can use to accurately foreshadow, given the robot was doing a certain action, this is what you would expect to happen to the objects it's interacting. With this challenge, because we're operating on a video level, this kind of opens the floor as well to using different techniques such as latent diffusion. The third and final challenge we have is the evaluation challenge. So this is taking kind of an accurate world model and kind of making it plausible to evaluate actual robot policy or general robot model. So if we can believe that you have a very accurate world model that could behave like a learned simulator, can it actually rank policies from good to worse? So the concrete challenge is, given you have 10 checkpoints of different policies, can you predict their best to worst performance when you actually go and evaluate them in the real world and you run the actual task in the real world and you score it based on success rate? So yeah, that's still to be determined. We haven't released the details yet, but if you can do this, we suspect that that would really kind of unlock the kind of scaling that Eric mentioned. So you can imagine that one use case you can use with evaluation, or how this kind of ties together, is that if you can accurately predict the value function, from a kind of reinforcement learning based line of thinking, which is kind of the future expected reward you would have given your current state, then you could kind of understand, how successful your policy might be, and you could use that to kind of evaluate your policy. So we've been thinking along the lines of this, and you can see in this task that we kind of separate this task out into multiple subtasks, where the progress or the value here increases, across each subtask. So by going higher, you can imagine that we would be more confident that the model is going to succeed at a given task. So across this kind of sequence of subtasks, we can kind of measure out the success rate that we would expect the robot to have, or maybe a given robot policy to have, without actually taking the time to manually do this annotation. We furthermore are looking into things like VLMs for auto captioning. So when it comes to understanding sequences, it's also important to interact with the multimodality nature of current language and VLM and kind of foundation models in general. And so if we could kind of auto caption our sequences and kind of automatically kind of annotate and understand what is going on in each sequence, in this case, the robot is packing a box with some kind of stuffing paper, then we could kind of condition on that and use that as kind of a conditional signal to both let the world model know what to kind of predict next, and also to let a policy know kind of what action it should also kind of desire to take. So we've talked about a lot of kind of different concepts. On the left side here, we have kind of perceptual thinking. So thinking along the lines of sequences of videos and understanding kind of what is in those videos. On the right side here, we have policy kind of understanding. So if you can, given a kind of a image or given a state, you can understand, what a robot should be able to do next, or what the best way to succeed at a given task is. And through this world model, we hope to kind of put this all together to be a kind of policy simulator and video generator that can take the richness of the kind of vision understanding with the kind of practicality of task solving and task policy learning, and kind of put that all together into a language and action and kind of robotic-centric kind of a multimodal model. So yes, if you're interested in what I just described, we have a lot of community resources, including a Discord, including a GitHub, and also a Hugging Face dataset. So feel free to check out all of those resources. And if you have a submission you would like to make, just email us at challenge@1x.tech. All right, I think that is all for us.
Well, that was awesome. That was very impressive all around. So many great questions and comments. I want to thank your team also for addressing a lot of those questions inside the chat. So if anyone who's watching there, we have hundreds of people watching. So thank you all for tuning in. But if anybody watching, definitely feel free to engage in the chat. A lot of great conversation, information being shared back and forth. We've been pasting links throughout. We will update the description of the video afterwards with some of these links, people who don't want to scroll through the chat. So that will be done. But really just fantastic work all around, very impressive. And this challenge also, I want to get one of these. I want to get one of these robots. I think a lot of people are very excited about the folding laundry or washing dishes.
Sooner than you think.
I think that's amazing. Very good. So much information. So for everyone out there watching, I just want to just remind everybody that this is not the only place where you can get the information. You can always continue the conversation either on the Omniverse community Discord server, which is discord.gg/NVIDIA Omniverse. We have lots of channels separated by topic, including topics like this. And we also have our official forums, which is a great place to ask any tough technical questions, or if you're having any feature requests or any trouble, you can post for official support there. But for community, the Discord server is a great resource. And a couple of people had asked questions about, well, can you use these applications to do more sensitive stuff regarding medical labs and things like that? We actually, on a recent live stream just a couple of weeks ago, we showcased a great group of students that did just that, actually, training the robots to handle delicate materials so the operator doesn't have to be there. So I highly encourage people to check out that live stream. It's on the NVIDIA NVIDIA Omniverse YouTube channel. Okay, so I want to pass it back. We've got a few minutes. We had a bunch of really fantastic questions. Let me circle back. I think our producer has been doing a fantastic job as usual, answering some questions along the way, but also putting some stars on some stuff. I think this is probably is worth repeating. We did discuss this a little bit, but just because I know this is a common question we get, and this is more meant for probably the NVIDIA team. But can you help kind of differentiate Isaac Sim and Isaac Lab? I think we kind of went over how Isaac Lab is specifically meant for training, but how else can we kind of just make sure it's super clear that what the difference is there? And this could go for, yeah.
Okay, all right. Thank you so much, Edmar. Yeah, I know that's the question everybody keeps asking. What's the difference between Isaac Sim and Isaac Lab? If you kind of remember the three key puzzle slide that we shared, so we said for three things that you need for robot learning, you need a simulator, like a generator or a data generator. So that's Isaac Sim. So Isaac Sim is actually where you design your robot, put all the pieces together. If you want to test how your robot works in simulation or generate data from your robot, that's the way it lives. That's Isaac Sim. That's the simulator. Now, if you now want to create tasks for robot learning, like for instance, for reinforcement learning, you need to design your observation, your action, your reward function, or for imitation learning, you want to design your policy. What is your architecture of the policy? What's the loss function, and all of those things that requires learning, or those learning taxing framework. So that's actually what Isaac Lab is a tax design framework that is based on Python. So it's a Python API to be able to interact with your robotic simulator. So that's Isaac Sim. So Isaac Sim is a simulator. Isaac Lab is actually where you design your stacks and then you have different training environments. So that's the difference between the two. Just also to be able to, because I saw a question about OIG and Isaac Gym and all. So in this particular case, for if you look at Isaac Gym ecosystem, so the simulator here will be Isaac Gym. The environment where you design your tasks is called Isaac Gym EMS. That's the environment, and then you also have another one which is OIGE. So in this case, what's the simulator? Isaac Sim. What's the taxing framework? OIGE. Omniverse, Isaac Gym EMS. So let's just say Isaac Lab is just the where you design your environment, or the EMS of Isaac Sim today, if that separates the difference between the two. Thank you.
That's awesome. That's great. I'm gonna save that clip, and I'm gonna have it on repeat on a Discord server so people can always go back and listen to that great explanation. We had a question here a little earlier about hey, when are new features will drop? So we don't announce new features until they're actually new features. So the best bet is to follow along with the live streams, of course. That's where we always kind of deep dive into the latest things, like we are today. Also, to keep up with NVIDIA blogs, and on if you remember Discord server, another great benefit is that we have a channel there that automatically posts the latest blogs as they come in. So that's a great place. Does anyone from the NVIDIA team have any other guidance besides what I'm saying, or is that pretty accurate for?
Yeah, thanks, Edmar. Do you want me to take this question on?
Yes, feel free.
VR0T. Yeah, so very recently, so last week we had Coral 2024, and we launched Isaac Lab 1.2 and also GR00T workflows. So we have a special blog just on that. Amelia or Edmar, if you could share it. Again, really, we started out thinking about GR00T initiative as, helping build foundation models. And through the process, we saw that there are so many different technologies coming together and tools that our ecosystem of partners have been building. We've been collaborating on some of the efforts as well, that it just made more sense to expand the project overall, which is why we have launched the workflows around perception, manipulation, mobility, group gen, or you could say GR00T, and Mimic, and so on. So it all starts with data processing and data generation, to mobility, to perception and dexterous manipulation, and so on. So we'll continue to add more pieces of the technologies and different tools, or different versions of our existing tools like Isaac Sim and Lab. Everything will continue to evolve. In terms of the cadence of the software releases, we just recently launched Lab. In the coming months, you could see another launch coming up for Sim and Lab as well. And obviously, if you haven't heard of our main developer conference, GTC, I would highly recommend that you join us there. We will have a lot of developer momentum around Sim, Lab, and all cool things with our humanoid robotics partners as well.
Ooh, I just muted myself. That is true. And also, we actually have great things in the works for GTC, obviously, as we do every year, including on the community side. So if you are planning to attend GTC, let us know so we can make sure to loop you into some of those things. We're always very excited to meet and engage. And also, if we can help you set up any meetings, either with NVIDIA folks or with partners. 1X, I bet you 1X will be at GTC. What, are you guys going?
I think we have a presence there.
You will.
Of course, we'd love to have them. Edmar, I do see another question associated with GR003. I could take that.
Yeah,
So
please.
the question is about, is there a way to access GR003 workflows without the need to apply for the humanoid developer program? So some of these tools like Isaac Sim and Isaac Lab that Oenda mentioned about, which is also very applicable to the GR003 project overall, is already available. So you could try and test it out. The workflows, there are certain models. If you take a look at the developer blog that we have recently posted, we have also opened up the code to certain components of it. Do take a look at it. Again, as we have more updates and as our partner ecosystem like 1X and the rest of the humanoid ecosystem will have new updates, we will be sure to relay that to our community. But so far, take a look at the group workflows developer blog and let us know what you think. And the exciting thing, Edmar, and probably you already mentioned about this, we will have a follow-up office hours. I know this is a lot for our first ever Isaac Lab live stream, but we will come back again. So next week, Oenda and one of our other colleagues, Savri, will be joining us to do all things office hours around Isaac Lab. So that's going to be a great follow-up session. So do join us next week. And Edmar or Amelia, if you don't mind sharing the link to our next live stream and all the details, that would be great. Thank you.
Yes, we'll post the add event link so that you can add that to your calendar, no matter what calendar you're using, you add it easily. But yeah, next week, I think it's going to be a little bit earlier in the day, but that's going to be a great question, a great time to ask your questions live. And it's just a week away. So today was a great precursor to that. Okay, so let me see. We've got a couple other questions here. Let me see. Some of them relate to the 1X team, I think. So on the, I think you guys actually may have answered some of these questions in the chat.
Yes, that we've answered pretty much all of them. I actually realized as well that our Discord link that we sent was outdated. Maybe I'll paste a new one in the chat.
Okay, great. Yeah, so anyone who's watching this video on YouTube, you can actually see a lot of the questions and answers in the live chat, which will be part of the stream forever. So let me try. I'm trying to see if there's something we didn't hit. I guess, I don't know, do we touch on this? This is a question came in from LinkedIn. Is there any cloud platform where we can use Isaac Lab?
Yes, we covered it already in the slides. So you have AWS, you have Alibaba Cloud, GPC that you can actually use to be able to train.
Perfect. There you go. Okay. Let me see. I do think we actually covered quite a bunch of these in live. Let me see. Let me see if this one might be a good one. It's coming from LinkedIn also. If you consider reasoning about affordances that the world model could handle to infer possible uses of objects. I guess this is for the 1X team.
Yes, I think we already answered that in the chat as well. Yes, we are thinking about handling affordances. We hope to get better at affordance understanding, the more kind of object and robot interactions that we train on, and we aim to randomize and collect diversity in that kind of object robot interaction to achieve this.
Amazing.
So, maybe let me add on to that. Generalization to predicting the future affordances is like any other generalization to something about the future. So along with predicting what happens to objects, you could also imagine that if we're trying to predict the outcome of a good policy, it should hallucinate the correct affordances of objects around and interacting with objects. And the beauty of building these kind of world models based on video generation methods is that it's very general and it can be applied to many kinds of subproblems in robotics, like affordance prediction.
Okay, fantastic. Thank you for that. Great information. Let me see. I think we scroll down a little bit here. This might be a good one. Is there a way to access group workflows without needing to apply for the humanoid developer program?
We already covered that. Thanks, Edmar.
Okay.
There's one other question. I could take this. I can share the screen because someone was asking about the humanoid robotics partners that we're working with. I can just bring back up the slide. One moment.
Okay, I'll bring it up. And we just have a minute or two left. So if anyone has any questions, feel free to post them.
Yeah, so here's just a quick snapshot again about some of the key humanoid robotics partners. So we have Fourier, Galbot, Menti Robotics, Berkeley humanoid team as well. So a combination of commercial robot makers and research platforms as well. And as you already know, 1X is also one of our key collaborators. And just jumping back in here, so the Isaac Lab ecosystem is growing. It's open source. We would love to have you give it a try. Come back next week. We would love to have you join our office hours as well. I see a few comments about, having an Isaac Lab study group and so on. So I'm sure our community team is looking into it. So would love to have you back next week to join us for office hours with Owen and our other colleagues.
That would be amazing. This time has just flown by. I want to just do a quick round. If anyone has any last minute kind of things they may have left out, I want to just leave people with, feel free to say it now or forever hold your peace. I think we covered everything.
Okay, I think one last thing we might just need to say is, I know everybody keeps asking about Orbit on the platform. So same thing, Orbit. The simulator is Isaac Sim, where you put the taxing framework is Orbit. Now, Isaac Lab is a combination of the effort of our different simulators over the years. So if you looked at, we defined two different workflows, the direct workflow, which is actually the OIG workflow, and then the management workflow, which is actually the Orbit workflow. So combining OIG and Orbit together is what we actually bring together to you as Isaac Lab. So Isaac Lab combine those efforts so that we can have developers that prefer direct base, put everything in one script, or you want management based like Orbit, put everything in different kind of submodels. So that's what we have for you in Isaac Lab, just to be able to clarify what Orbit is versus Isaac Lab versus Isaac Gym versus OIG and all of that. Thank you.
Super helpful. And I see SyncTwin is here. So that's Omniverse Ambassador Michael Wagner. I think Shane Reitz is in the chat. He was on a live stream recently from Loop, another great company leveraging OpenUSD for robotics. Okay, any other last minute comments? Yep.
Yeah. Edmar, I was going to say that, there's a lot of information, right, in our live stream. But again, the 1X challenge seems exciting. Would be good to kind of reiterate the deadlines that the challenge is tracking towards. Maybe, if you want to reinforce that, Eric and team, that would be awesome.
I can take that question. Yeah, thanks for asking. So the first two challenges are released and the criteria are open. The first one being a sort of rolling basis. Anyone can submit a submission anytime to compete in the challenge. To date, no one has claimed yet the $10,000 prize because we've set the bar to a level that we think is achievable, but not trivially easy. So we're excited to see how far people can get on the compression challenge. The second challenge for sampling is a bit different in the sense that you're not going to be submitting us your code and we rerun it on our validation set. Instead, it's going to be a evaluation server that we'll open up in March of next year. And we'll send you some initial images, and then you'll send us back the video of our across test cases, and then we'll score the generated video using our metric. We'll release the metric in March, and the idea of this is just so that people are broadly working on improving the sampling, but not over optimizing for the sampling metric that we're releasing. And the idea is that we'll judge the best submission by around May or June of 2025. The exact kind of cutoff deadline will be announced in the future. Is that clear?
Yeah, it's great. Awesome. Gives people plenty of time. That's great. Okay, well, I think that wraps it up for us today. Definitely feel free to continue the conversation on our Discord server. Hop on over there, discord.gg/NVIDIA. As we mentioned earlier, the office hour is going to be next week. So check out that link. We'll go to our Ed event calendar. Have any questions, anything, you missed anything, you can hit me up on Discord, Ed Mendy, EDMENDI, and I'm happy to help you. I want to thank each of our guests for the amazing materials presented today, the great expertise and sharing all this wealth and knowledge, especially 1X. Thank you for really opening the doors to your projects and sharing so openly and answering the questions from all the developers watching the community. And of course, I want to thank everybody out there tuning in from whatever platform you came in from. Thank you for watching and make these live streaming so fun. If you have a topic you'd like to suggest, please feel free to reach out to us anytime. And if you are an expert in one or more areas of OpenUSD or Omniverse, feel free to get in touch with me, because we are always looking for Omniverse ambassadors from the community. So people out there that we can celebrate and promote your work and introduce you to partners and customers and clients and friends. So if you think you'd fit as an expert in one more areas, definitely feel free to get in touch with myself or our amazing producer, Amelia, and we'll help you with next steps. That being said, thank you, everybody. We'll see you next week for the office hours. Until then, I'll see you on Discord.